Hi, this is Sai Vamsi. I'm here to talk on the paper Serverless Linear Algebra, which proposes a design to run dense linear algebra algorithm with matrix of size 1 million cross 1 million on serverless programming model. Let's go ahead and look at the problem statement. We know that for computation intensive algorithms, which also require data transfer between executions, it is difficult to run them on serverless platforms due to latency and overall inefficient throughput. Below figure shows the available parallelism, that is the number of cores and required working set size over a time in a distributed Cholesky decomposition. As we can see, Cholesky decomposition requires high resource availability during early phase of execution, and the availability keeps drastically decreasing over the course of the execution. These type of algorithmic computations can be better run over serverless programming model, which provides elasticity to the resources available. Author has proposed a design called NumPy. Application designers who can clearly separate program state and logic can avail serverless platforms, provide instant access to large compute capability without the overhead of managing a complex cluster deployment. By proposing NumPy, it executes programs written using LambdaPack, a high-level DSL that can express arbitrary tile-based linear algebra algorithms by decomposing programs into fine-grained execution units that can be run in parallel. NumPy analyzes the data in LambdaPack and extracts a task graph for parallel execution. It then runs parallel computations as stateless functions while storing intermediate states in a distributed object store. Operating on large matrices at fine granularity can lead to very large task graphs. So author used loop optimization architecture to infer task dependencies which are on demand from the original looping program rather than unrolling it. In doing so, he showed that LambdaPack at runtime can scale to large matrix sizes while generating programs of constant size. These are the couple of novel points that I found out during the course of reading the paper. The author's novel design, NumPy, computes linear algebra workloads on serverless architecture. Per author, NumPy is the first large-scale linear algebra library that runs on a serverless architecture. In the paper, NumPy is made to run on Cholesky decomposition of size 1 million cross 1 million matrix and came within a factor of 2 wall clock time over Scala-Pack, which is an existing MPI-based architecture running on a dedicated cluster with the same hardware and number of cores while using up to 15% less total CPU hours and providing fault tolerance. It requires communication in parallel commuting, and since cloud providers place limits on the use of each resource to efficiently manage resources, it has become a constraint to the design principle of NumPy. Author has proposed a novel idea by storing intermediate state during computation in a distributed object store. The services which available are S3 or Google Cloud Storage and still achieve the same bandwidth as if it were accessed from other nodes RAM. With the help of AWS SQS or Google Task Queue, control plane state like task queue is shared between all serverless function invocations. Authors have designed LambdaPack to express linear algebra algorithms as directed acyclic graph-based computations. LambdaPack borrows techniques from DAC execution framework, but unlike DAC, LambdaPack does not require the user to pre-specify a DAG of linear algebra kernels, which is a novel method adopted in the paper. Author adopted a novel idea of fault tolerance protocol, which keeps running programs in a valid state even if workers exceed the runtime limit and are killed mid-execution by the cloud provider. These are the list of important points are identified during the read of the paper. Author through this paper has tried to achieve dense parallel programming on serverless computing, whose demand for resource varies dynamically over the period of execution. Lee's mechanism has come in as a fruitful mechanism for effective failure detection and recovery. Performance evaluation revealed that NumPy reads more number of bytes of data over the network because of each state being stateless and need to access all its arguments from a remote object store. Disaggregated storage allows NumPy to have the flexibility to run with 4 times lesser cores but increases the completion time by 3 times. NumPy can provide good performance even for problems that fit on a single machine while also scaling to large problem sizes. Proposed design handled fault recovery, auto scaling for effective utilization of resources very well. When it comes to scope of improvement, data red is an important area of concern that has been identified in the proposed approach. We see that existing MPI-based scale-up systems, which run on static cluster of resources, read almost 21 times and 6 times lesser data when compared to NumPy over QR decomposition and GEMM algorithms. For algorithms having fixed amount of parallelism, the excess communication in NumPy leads to higher resource consumption. The factors used in the design of scaling factor and timeout factor were calculated by using simple heuristics, but the values of these parameters need to be chosen more accurately as the two determine the effective resource utilization and throughput. The author has executed the following communication avoiding Cholesky algorithm on a serverless lambda packs design system. The 3 for loops are run in a parallel computing mode. This is a broad architecture of NumPy. As we can see, the tasks will be assigned to task queue, and a provisioner will provide help in providing the tasks to executors, which are AWS Lambda service. AWS Lambda service gets the data from object store, which is S3 or DynamoDB or Redis. These are the performance comparisons between NumPy and Scala-Pack. We can see that CPU time for NumPy is hugely less when compared to the existing Scala-Pack. So this is about the serverless linear algebra. Thank you.